Today we have Marta Pedroni here from the University of Geneva, and she works on singularities. And today she'll be talking about singularities in quantum gravity.
Thank you very much, and thank you very much for inviting me here. Today's topic is limit of singularity resolution with quantum gravity. Actually, when I say loop quantum gravity, very ambitious and maybe a bit more advanced than what I'm gonna be talking about in this talk. I hope I will be able to cover all the material, but still somehow reduced. So there are four main parts of this talk. So these four main parts also divided in two main actually half of the talk. So in the first half, in the first two sections, I will provide kind of like a general analysis of singularity resolution in loop quantum gravity, but starting from what it means to solve space-time singularities and kind of like general criteria to solve, to establish the occurrence of singularity resolution. And then in the second part of the talk, I will try to go more in depth, or better to apply what I proposed in the first part to a specific case study, so the Big Bang singularity in loop quantum cosmology. And so let me start actually with even bit more general question. So what does it mean to solve singularities in general? This is important because it helps us to better understand the meaning of space-time singularity. Because of course there are some analogies, but there are also these analogies. So I mean, singularities are something that kind of spread in physics. So we find singularities in different theories and different contexts in physics. So for example, in electrodynamics, in transition, and even in classical mechanics. So we can ask for kind of a general definition, characterization of singularity. And this general characterization is usually provided in the form of, referring to infinities. So the idea is that singularities are points at which some physical quantity becomes infinite or undefined. And so, for example, in the electrodynamic case, if we take the electric field of a point charge, we find a singularity at the location of the charge. So when R is equal to 0, the electric field goes to infinity. And in the case of phase transition, we find infinities at critical points, and so on and so forth. And even already in this situation, we can kind of try to answer what it means to solve the singularity. So the solution is in the form of a kind of redescription of the phenomenon. So the phenomenon is described by a different theory, more fundamental theory maybe, or through a different technique, which eliminate the singularity. So what it means is that the kind of it eliminates the infinity. So we don't have these infinite quantities anymore. And it actually takes the form of a correction of the predictions of for example, in the electrodynamic case, we have this prediction of the theory of having a singularity at the location of the point charge, and then we have QED, in which basically kind of redescribe the phenomena, and thanks also to renormalization, it prevents the rising of infinity. So it gives different predictions. It doesn't mean that we're going to have infinity at the point charge, which in fact is not something that we observe. And the idea is that this correction of the prediction can be expressed. It's usually expressed by the idea that the singularity model is valid up to a point, and we have a breakdown of the theory. So how this applies to the case?
Question. So at some point in time, Einstein thought of singularities as placeholders for matters. But I don't know how to model an electron or a muon, but you can pretend they're singularities and work with them. Would you call it solving a singularity? Because you're not eliminating them, you're using them. They would say, well, that's fine if I did it, but you just don't call it solving. Why do you want? Do we need to solve them? Are you saying that?
I mean, yeah. So this is a different question. I would say this is not the solving a singularity, but at the same time, I mean, the claim is down that all singularities must be So the idea is that since we have this claim of singularity, well, space-time singularity resolution in quantum gravity, what does it mean? How we should understand?
Yeah.
Could you say a bit more what you mean by correction of the predictions?
Yeah. So, for example, like, so let's take again the case of electrodynamics. So the prediction of the theory is that there is, well, the field goes to infinity at the location of the point charge, and in theory, this prediction is correct in the sense that we don't have the same description. We have different description, and as a matter of fact, I mean, we don't observe infinities at the location of point charge. So in this sense, another example could be, even though it's slightly different, the black body radiation, the ultraviolet catastrophe. This kind of like prediction that, I mean, we don't observe, and we have a correction of the prediction in the sense of an explanation of why we don't observe these. So what does it mean? So space-time singularities. The first thing we should observe is that the notion of singularity is different in the case of GR. So we do have singularities in GR. We actually know that they're kind of like, they appear in several models, so they're kind of like a generic prediction of GR. However, these characterization as singularity as points at which physical quantity becomes infinity is not completely correct, or I would say like it's not correct in the case of GR. And it's because space-time singularities are not point of space-time, they're not point in space-time. What I mean, we can understand it with an analogy again with what happened in other physical theory. So for example, like imagine if the electric field of point charge, we can say at the location of the point charge, and I can also like kind of like points where it happened according to electrodynamics, we have a singularity. And I can say that because there is like a background spacetime over which the field lives. But this is not the case in spacetime. With spacetime singularities, because in that case, spacetime itself is singular. And this, I think, this idea is well expressed in this quote by Ofer and Callender. So the singularities are singularities in the metric space itself. So there is literally no location for the whole. Fields on spacetime can be singular at points, but spacetime itself has nowhere to be singular. So this idea of a point at which we have infinite physical quantity cannot be kind of like directly applied to the case of spacetime.
Can I ask something about this one statement? There is no location for whole. But it is the mere absence of a single space-time point, right? So the absence of the space-time point is the whole.
Yeah, but I mean, the point is that there is no absence of a space-time point. So by definition of like what space-time is in GR, space-time is a continuum, smooth manifold. So like the smoothness means that there is no missing points of the space-time. So there is a sort of idea of singularity as missing points, but they cannot be like space-time because of the way in which we define space. Yeah.
Yeah, but you can sort of in space-time approach it.
Yeah. So
there's no location is still a bit weird.
There is no
approximating with arbitrary accuracy.
Yeah, I do have a side project in which I see like there is a way to localize in some sense singularities, but like if we are asking for a point at which a singular point, so a point in space in which we have infinite quantities, that's not just like not doable because of the way in which the theory is constructed.
Yeah. So this case it has to do with the fact that you have a metric, or is it independent? Even the manifold, we would also have the distinction between space-time similarities and the other similarity. Because I can understand in some way that okay, the metric is the one that is singular, then of course you can't really talk about structure that singular whole because you have anything to measure. Then I understand. But then if you assume the space-time is just a manifold, would you, because you were saying something that it destroyed the smoothness of the manifold?
Well, the metric is smooth as well.
So yeah, but so I'm trying to understand what's the difference between this space-time singularity and the singularity that you think like before. So if I'm talking about an electric field, I say, okay, it's divergent at a point. I could see, okay, also the metric is divergent at that point, so they are similar. But then you say, well, no, because the metric takes some space-time meaning, and then you're breaking that by this thing, so it's different from the electric field. I understand this correctly.
Yeah, I mean, I'm not sure I understood the question.
So what makes the space-time singularity different from the singularity of an electric field? Is it that because the metric is singular?
I mean, it's because it's space-time is singular.
So what do you mean by space-time?
I mean, what I mean is the metric and the manifold, and then they taken together. But yeah, I mean, like, also if you just mean the metric.
Okay.
Okay, so we have actually two different notions of what singular behavior is in GR. So if we try to define, I mean, like the task of defining space-time singularity is very difficult, and I would say like there's no consensus. Like this is still kind of like an open debate, but we have like two main notions. So the one is in terms of curvature blow up, and it kind of call back to the notion of having infinite physical quantities. So the idea is that the space-time is singular if and only if a curvature scalar invariant fails to approach a finite limit within a finite affine length along G. So basically, we have a quantity, especially in this case the curvature, which goes to infinity along the infinite time. And the second notion is the notion of geodesic incompleteness. So the idea is space-time is singular if and only if it contains a maximally extended curve, specific case geodesic, which still ends after a finite amount of rapid time. So we have two notions. One is curvature law, the other is, let's say, incomplete curves in space-time. And well, one thing you should notice is that, especially the second one, but both conceptions actually kind of like shift the notion slightly. So there is a conception of singularity in terms of global properties of space-time, so kind of adjectival conception. So we talk about singular space-time. And second thing to notice is that these two notions are not logically equivalent, of course. They are not conceptually equivalent, they're different concepts, but they're also like not extensionally equivalent in GR, in the sense that we have some space-time, singular space-time, which can be kind of like labeled under the idea of curvature blow-up. So we have these curvature singularities, but these are a subset of the space-time that are singular because of geodesic incompleteness. So we have some examples in the literature of space-time they are geodesically incomplete without there being any blow-up. In other words, there are incomplete curves, but there is nothing wrong with the curvature. So it seems like, for example, like if you're an observer in space-time, you might just kind of like, let's say, end up in the singularity in the sense of like at some point your trajectory finish without there being any real, I don't know, tidal effect or anything wrong with the curvature. So let's go back to the question of what it means to solve. I mean, we go back to these two different notions and now they play out in the quantum context later. But now let's go back to what it means to solve space-time singularities and identify, well, two main ways. So the first one is replacement. So to solve a space-time singularity means to replace is kind of like similar to the idea of, to what happened in other physical theories. So the idea is that as in other cases in physics, we have singular model, singular model, which is replaced by a non-singular, more fundamental model. So in the case of space-time singularity, GR and theory of quantum gravity, which provide the less fundamental model up to a point. And as before, this seems to imply that there is a correction in the prediction of the prediction of GR. So this is kind of like how this can be represented. So we have like kind of like two different levels, the GR level, we have singular models in GR, which are replaced by non-singular models in quantum gravity. And as before, it seems to indicate that the singular models are valid up to a point. So there is a breakdown of the theory, which is to be identified with the singular structure. So the breakdown happens. It's the sign of the breakdown is the singular structure. So it has to be eliminated, replace it at least on the fundamental level. This is kind of like I would say like the standard idea, even though it's often like kind of implicit in the physics literature. I want to focus at the moment on up to a point. So what it means that there is some sort of correspondence between the two models. So like the non-singular model is kind of like possibly quantization of the singular model, but there is some breakdown at some point. And in particular, it seems like the correspondence breaks down as concerning the singular structure. I will explain better what this means and how it is applied in the case of singularity solution in the next session. And the second way, general way in which space-time, we might say that space-time singularities are solved if the arising of singular behavior is just prohibited. So we impose some external constraints that kind of like rule out, to begin with, some of the singular models. So for example, let's suppose that we say like, oh, the physical models of GR are just those global hyperbolic, then some of the singular models are just ruled out by fiat. So there is a restriction on the solution of GR. And I kind of adopt a permissive view in the sense of like, I think that singularity solution should mean the general avoidance of singularities in either form. So it can be like by replace them. It can be by kind of like preventing singular behavior to arise. Now let me focus on what it means to replace.
So can I ask a question?
Yeah.
How does Crowther and Heil have this paper on singularity resolutions?
Mm-hmm.
And they mentioned 4 different attitudes. And one of them seems to be saying that you're replaced. But then another one is saying singularities are resolved classically. I thought that was going to be the same as prevent, but it doesn't really seem to be. But they are not necessarily saying, well, just rule out all the singular solutions as unphysical. Or at least I think they're saying add some matter fields or show why such solutions approximate more realistic solutions. Without singularity, remove idealizations. So that seems to be what there. I guess I'm asking, is that the same as or the same, or is that a
I don't think, in a sense, I don't think it's the same because like the preventing strategy. What I will argue in this talk is that actually, like in loop gravity, we have both strategy playing out. So like the preventing strategy doesn't mean like eliminate any type of singular behavior, like ruling that out kind of like a priori or by inputting constraints. It can be like it can mean ruling out some types of singular behavior, and also like I think like I say like by the imposition of some external conditions, and this imposition can be kind of like motivated classically maybe, but also like motivated by it, other theories beyond GR. So it could also be motivated to quantum.
Yeah, I guess I'm thinking maybe they're actually just kind of the third option in the sense of like they use internal conditions or it's internal methods. So, anyway,
Yeah,
okay.
I mean, I don't know if there is like a one-to-one correspondence with the different attitudes. I don't even think like, I don't think that these strategies should be interpreted as attitudes toward the singularity. I think they should be just like, way to understand like, what does it mean to solve this singularity? So like how, let's say like, which general form can have this solution? And one general form is the replacement and one general form is like kind of like ruling out. I think like different attitudes can be compatible with these two general properties. So to the second session, how to establish singularity resolution. I provide 3 general criteria. So the first one has to do with the violation of singularity theorems. So of course, if our idea of quantum gravity wants to solve singularity, it should kind of deal with the singularity theorems that we have in GR and explain why they don't apply. But well, at least they say, maybe not explain why, but the singularity theorem shouldn't apply to this new theory. The second one has to do with the examination of the breakdown of classical correspondence. So how this breakdown in the replacement strategy is to be understood. And the third one concerns the individuation of the assumptions and the conditions for singularity exclusion. So in quantum gravity, in the specific case of blue quantum gravity, what are the, let's say, the physical mechanism behind singularity exclusion? How do they explain the resolution occurrence? So the first one, violation of singularity theorems. Well, let's start by looking at singularity theorems in general relativity. They usually have like 3 conditions. The specific condition can vary, but they usually have 3 or 4 class of conditions. So the first one is an energy condition. The second one is a causality condition or a condition on the behavior of geodesics in some point in space-time. And the third is a condition on the global structure of space-time, usually. This picture taken from Pedroni's 1964 paper, so the first singularity theorem. And what the theorem says is that the space-time satisfies the weak energy condition, so no observer can observe negative energy. There is a trapped surface, and the space-time is global hyperbolic, then the space-time is geodetically complete. So one thing to notice is that the conclusion is geodetic incompleteness. So this is kind of like the notion of singular behavior employed by the theorem. And these correspond to the kind of like they are the specification of the general condition that we find singularity theorems. So what happens when we go beyond GR? Usually, what we the condition put under question is the energy condition. In fact, actually, the violation of the energy condition is kind of like expected in the quantum context, and actually, I mean, it's also empirically confirmed in some by some experiments. So these negative vacuum energy is observed in quantum field theory and so on. So the idea is that singularity theorems might be violated in the quantum context. However, there are some results in semi-classical gravity, recent results, that provide semi-classical theorems, semi-classical singularity theorems. So what do they do is to replace the energy condition with the generalized second law, which states that the generalized entropy doesn't decrease. And instead of instead of a trap surface, they use a quantum trap surface, and they have global hyperbolicity. And the conclusion, as before, is that the space-time is geodesically incomplete. So even in the semi-classical regime, it seems like we have some singularity theorems that indicates that there is some singularity behavior. This is unexpected, but I mean, still, what does it mean for loop quantum gravity? So this, at the semi-classical level, the question is what happened beyond the semi-classical regime? Should we believe that the assumption of the semi-classical theorem still holds? Well, we can already put in question the generalized second law, in the sense that it depends, for example, on Lorentz invariance. So who knows what happened to Lorentz invariance? But also, I would say, like, if we have a quantum space-time, it's not clear that any of the other assumptions holds anyway. For sure, there is no singularity theorem formulated beyond this classical regime. And in a specific case of quantum gravity, I don't think we have strong reason to think that the semi-classical theorem still holds, because, for example, we have spin networks, which are the fundamental entities of the theory, which are quantum discrete, which represent the quantum discrete geometry, and they have quantum properties such as superposition and indeterminacy. So it's not clear whether the say geometry of space-time is such to support things like causal structure, or even to define global hyperbolic. And I mean, moreover, we have some. I mean, it's often said that space-time disappears at the fundamental level in loop quantum gravity. So it's not clear how to define or how to talk about the some general space-time properties in that case, and it's not even clear what the geodesic could be. So if the conclusion is something like the conclusion of the theorem in general relativity and the conclusion of the theory in classical gravity, so that the space-time is geodesically incomplete, it's not even clear what this would mean in quantum gravity, because the notion of geodesic is not defined. Of course, it's still possible that we could formulate a theory, a singularity theorem by modifying some assumption or by tighten from scratch. This kind of like still open. So there is no theorem that is not, doesn't mean that it's impossible to provide such a theorem. But the burden of the proof is on who wants to elaborate such a theorem. So there is not here at the moment, and it seems like the theorems that we have in general relativity and in classical gravity don't hold in the case of loop quantum gravity. What's the upshot of the violation of singularity theorem? So what does the non-applicability of the theorem show? Well, what it shows is that it is not the case that the occurrence of singularities is generic in loop quantum gravity. So what the theorem shows in the case of GR and some classical gravity is that the occurrence of singularity is generic. So the fact that they don't apply just simply means that it's not the case that the occurrence is generic. But of course, the non-applicability doesn't show that the singularities do not occur in loop quantum. So to show that the singularities do not occur, or to argue that the singularities do not occur, we need something stronger. So we actually need like a proper singularity resolution. And this brings us to the second point. So what even means to have singularities in the quantum setting, so in the loop quantum gravity setting? So the two notions of singularities in singular behavior in GR, again the curvature blob and the geodesic incompleteness, are something can be kind of spelled out as a more local notion and more a global notion. So local curvature pathology and global dynamics. And this is what it also is done by Thébault in his paper on the big band singularity resolution in loop quantum cosmology. We can provide actually two analogies notion of singular behavior in the quantum context, and is done both by Utrecht and Thibault. So the first one is concerning the divergence of relevant physical quantities, and it's analogous to the first one. And the second one concerns the breakdown of the equation of motion or dynamical evolution, and it's analogous to geodesic incompleteness. So the two notions can come apart in GR, this is what we have seen before. The question is if they can come apart in the quantum context as well. So how should we understand these two notions, these two quantum notions? And the idea is that one is a kinematical notion, so it has to do with divergence of physical quantities, and well, the, let's say, solution, I put it equal, but it's not equal. So the, let's say, non-divergent of physical quantity would be in the expressed by the finite expectation values of the observable in the quantum case. And the second one is a dynamical notion. As a matter of fact, has to do with the breakdown of dynamical evolution. So the two are logically equivalent again. And the question is whether they're extensionally equivalent or not. I think we don't have a good answer at the moment. So I think that both aspects should be considered in discussing singularity resolution. And as a matter of fact, Thibault, when we discussed the singularity resolution, the Big Bang resolution in the context of quantum cosmology, we'll see it after, but he considered a necessary sufficient condition for both notions. So having these quantum notion of singularity resolution help us to understand how the correspondence break down. So the idea is that we have singularity resolution when the correspondence break down between the classical and the quantum notions in the between GR and quantum gravity. So I put again the drawing from before, in the sense that now we can understand in what sense the corresponding breakdowns as concerned the singular structure. In the sense that at the classical case, in the classical level, we do have in the singular model the aspect of singular behavior is described classically, so we do have correlation gap and geodesic incompleteness. But at the quantum level, we don't have. I mean, if the claim is that the singularity is solved, then we shouldn't have neither divergence of relevant physical quantities nor breakdown of the dynamic evolution. So the still remains open question. So the example, like how we should properly specify the quantum characterization of singular behavior. So I said that in the case of divergences, I mean, we can say that the divergences do not occur if we have finite expectation values of all observable or of the relevant observables. What about the global dynamics? Another question is whether the correspondence, so this idea of breakdown of correspondence as concerns singular structure but not as concerned other things, implies a specific derivation of general relativity from quantum gravity, or yeah.
So you changed there. So you say now breakdown of equations of motion, dynamical evolution, but before you had unextendable curves. So you substitute this to not. You just interchange them like equivalently in this sense. So because for me, geodesic incompleteness has to do with curves, which usually are defined like idealized particles, point particles. Whether now you're talking about dynamical behaviors of fields, this is a different note, and it could be that even dynamics of a field, it works fine in a singularity, although you have to this incomplete.
Yeah, I mean, I think so. The point is that they're analogous, but they're not the same.
Yeah.
So then, like, one point is that we don't have. I mean, if we go all the way quantum, we don't have geodesic because we don't have trajectory. So of course, like, we cannot use geodesic incompleteness as a criterion. And what is, I mean, of course, it's also my proposal, but it's what is standardly done in the literature is like to understand these global dynamics notion of singular behavior that we have at the classical level specified as geodesic incompleteness as breakdown in the dynamical equation in general.
But then I could ask the question like, why would you even need quantum gravity if it could be the case that, for instance, the dynamical evolution of a quantum field in classical GR, of course, completely fine. There is no singularity. So you are using the fact, you're starting with the fact that there is geodesic incomplete. But then when you say you go to quantum gravity, you change the requirement because it's not well defined. So you go to the dynamics of quantum fields. Could it be possible that even in classical GR, then if you use that kind of requirement of the dynamical evolution very nicely, that it GR behaves nice or not?
Yeah, I mean, I'm not sure. So, like first of all, like these kind of like in general criterion. So I don't have in mind any like specific dynamic evolution of quantum fields. It's just like the dynamic evolution, let's say, of the theory. And yeah, I mean, I agree that it's different, but I agree that in a sense, this is stronger than geodesic incompleteness. But yeah, I think it's kind of like the only way to go when you go to quantum, because in a sense, like to verify whether you have a singularity. Well, the kind of singularity you can have dynamically is not singularity in the trajectory of things, in a sense that, like, especially if like what you have in the theory is quantum space-time, is the singularity you can have is singularity in the dynamics of the evolution of the quantum space. Right? So yeah, no, I mean, I completely agree that of course different notions, but it's kind of like a force move because you're kind of like switching.
Oh yeah, I understand. Like in terms of like quantum gravity community, it's like trying to solve this problem, and they do us again. Let's say, but then I wonder how, even if you solve in some way this quantum gravity problem, first of all, yeah, how?
Yeah, no, I mean, like you can see, your point is like, oh, I can still have like incomplete geodesic in the classical space-time.
I wonder if the second requirement is just because they say, well, the second point I want to solve comes from the fact that in VR we have this geodesic incompleteness, so I have this motivation. But I wonder if this is just too strong, and maybe this strong requirement is just satisfied in VR in general. So because it's just having, maybe you're just using classical point particles as your test particles, and then you get the variance. Yeah.
But I mean, in a sense, like if you have geodesic incompleteness, there is some disruption in your equation of motion in GR at the classical level.
Yes.
What means
Can we talk about this?
Yeah. Yeah. So, and another open question is how to check whether the correspondence breakdown in the theory, so in general. I will try to answer to some of these open questions in the rest of the talk. Some of them I just open. So the third point is evaluation. The third, say, strategy to assess singularity resolution, general strategy, is the evaluation of assumptions and conditions that plays a role in singularity resolution. So the general methodology that we can apply is first try to individuate necessary and sufficient conditions for a singularity resolution, maybe for like specific singularity resolution, so in the case of the Big Bang singularity. Then provide an analysis of the mechanism for singularity resolution, so how does the mechanism fulfill the condition that we have identified before, and then discuss the assumption. So, well, individual assumption and discuss the assumption. So we should discuss whether the singularity solution follows only from the construction of the theory, so from the principle of the theory, or if there are additional assumptions, and whether these additional assumptions are justified. So I will try to apply this methodology to the case of Big Bang singularity solution in the third section of the talk. But some part of this methodology is already present in the literature. So, for example, like again, referring to Thibault paper, what it does is to provide an analysis of the resolution of the Big Bang singularity in quantum cosmology, and it identifies some necessary, sufficient, and necessary sufficient conditions for the solution of the local curvature notion of singularity or the global dynamic. And it does so by using the notion of classical correspondence. So the idea is that a necessary condition fails to apply. Well, necessary condition fails when there is a model in which the condition does not obtain at the quantum level, but still the singularity is solved in the sense that the correspondence breaks down. While for the sufficient condition case, it fails when the condition obtains, but it is not sufficient, so the correspondence still holds, so the singularity is not solved. I will kind of like have in the background of my presentation this work on necessary sufficient condition by Thibault, but I kind of use different sound conditions. For example, in the case of finite expectation values and bounded operator, I think these are, well, especially the bounded operator, I think it's necessary, it's sufficient, and well, the finite expectation value is necessary and sufficient for the local curvature resolution. Because what it does is to apply the condition, like the condition should satisfy actually both notions. Well, I think that we should study the condition on the specific notion. So the other aspect of the methodology is the mechanism for a singularity resolution. What does it mean? So what I mean with mechanism, there are actually two different aspects to this point. So the first one is to understand what is the cause behind the resolution of singularity and how this cause explains the occurrence of singularity resolution. So, for example, like I'm not claiming like any of these is actually a good example. Well, I'm not claiming any of these is actually relied, let's say, as a mechanism. But examples are, we can take discreteness as a mechanism in the sense that discreteness could be the case behind singularity resolution. It can also explain how it's realized, or we can take other contact pairs, we can take new constraints, or the existence of extra dimensions. Another aspect has to do with the physical interpretation of kind of like these mechanisms. So how we should interpret the non-singular phenomenon that replaces singularity. And here there are other examples. And these are things that have been done in the literature. So interpretation in terms of bounds, or as a quantum tunneling, or a phase transition, or as a boundary. So what I mean mechanism, I mean kind of like both aspects. So there is a kind of like a more formal aspect of how the resolution takes place, and there is also kind of like a more interpretational aspect. So how we should understand the like on the physical level. So even here we still have some open questions. So one question is whether we can provide necessary sufficient condition in general for a singularity resolution, because it seems like methodologically what we do is to kind of like consider a specific example of singularity resolution. So it's kind of like singularity dependent analysis. And especially, I mean, this is what is done in the case of Thibault paper. Another question is whether, I mean, what are the relations between the different conditions? So whether we have kind of like cross implication between conditions that we use for solving the blowout and conditions that we use for solving the global dynamics or not. And well, another question is how to determine whether the conditions obtained in the theory, so in general. And the hope here is that, like, if we actually are able to analyze the mechanism and study the mechanism, we can also discuss whether the mechanism is kind of like a general mechanism that is realized in the theory or not. So now onto the second part of the talk. Okay, I will try to be quick. So let's start with the facts. So the results that we have concerning singularity solution loop quantum gravity result that regard the Big Bang singularity and the black hole singularity. We have like several papers. These are like 2 reviews papers on the 2 aspects. The question is why. One answer is kind of like more maybe psychological, sociological. So like these are kind of like the 2 similarities that most bother us, because they're kind of like more realistic example of singularity. So we have good reason to think that, well, at least like in the GR, in the classical setting, we have good reason to think that there are Big Bang and black hole singularities, because we do observe some object that really looks like black hole in the sky, and our universe seems to be well described by models contains a Big Bang singularity in the past. So these are kind of like the examples that we would like to solve, because these are the most plausible, let's say, example of singularities at the classical level. Another answer is that actually they're both example of singularity of strong curvature singularities. And this is important because in the case of strong curvature singularities, the 2 notions at the classical level coincide. So the strong curvature singularities are both curvature singularities, and they also exhibit geodesic incomplete. And also, well, a general hope is that the quantization can cure the divergence of physical quantities. So since this singularity are curvature singularity, it seems that at least the curvature blow-up part can be taken care of by quantization. The question is, how are these singularities solved? I was planning to actually discuss both solutions, but I don't have enough time. So I will discuss only the Big Bang singularity solution in the specific context of loop quantum cosmology.
We interrupted you quite a lot, right? So
but so the loop quantum cosmology is a symmetry reduced version of loop quantum gravity. The studies models are isotropic and homogeneous, so it's often said to kind of capture the cosmological factory of the theory. And one important result that loop quantum cosmology takes from loop quantum gravity is that the area operator is discrete and have a non-zero meaning. So we have this called area gap, which is expressed by this formula. Because of the area gap, the curvature operator is defined by using finite holonomies. And this means that basically the operator is bounded and has a finite expectation bound. So even though, like, classically this quantity diverge, in the quantum case it's bounded. So it doesn't diverge. So this seems to solve the singularity at the kinematical level, because the relevant physical quantity do not diverge. What about the global dynamic level? Well, loop quantum cosmology is able to obtain is actually, like in loop quantum cosmology, we have exact solution of the Hamiltonian constraints, and like these, the one that we have in a fully isotropic model, and the Hamiltonian constraint become a difference equation, not a differential equation anymore, which just govern the quantum evolution of the physical states, and the relevant consequence for singularity resolution is that the equation doesn't break down at zero volume. So actually, like we don't have any disruption in the equation describing the evolution of the quantum state. Moreover, we can take the semi-classical limits of the equation, and we get a modified Freeman equation, which is such that even at the semi-classical limits, the evolution doesn't break down. So what it means, like the physical interpretation of this mechanism, is that the effective repulsive force when the curvature approaches the Planck scale basically overcomes the gravitational attraction. So we do have, so the quantum effect is that we do have a repulsive force that makes the universe expand again. So we have this bound. And yeah, this is a sort of representation of this bound. So like we have, also because we can take the semi-classical limit of that equation, we do have kind of like the classical description of the universe up to a point. Then the quantum effect becomes relevant, and the evolution, like through the bounds, is described by the quantum evolution equation. And then on the other side of the bounds, it seems like we have a kind of like mirror classical universe. Since the evolution remains well defined through the bounds, while in the case of classical theory, the evolution breaks down. So we have the Big Bang singularity, we have the breakdown of classical correspondence, and this indicates that we also have a singularity resolution as concerned the dynamic motion. So this is how the resolution of the Big Bang singularity is usually explained in the literature in loop quantum cosmology. The question is, what is the specific mechanism in play, and what are the additional assumptions that we should consider, if they are, and whether they are justified. So the main mechanism, well, at the first glance, we can say that the main mechanism is just the discreteness of the quantum geometry. So we have quantization, and we are quantizing background theory. So the question is whether the discreteness just entails singularity resolution. So whether singularity resolution just follows from this specific principle of quantum gravity. And the answer is no, but still there is kind of like indirect implication here. So the existence of the area gap is what kind of like implies that there is a single curvature in the case of the blow up. So because of the area gap, we have that the curvature is represented by holonomies, and hence it's like the operator is bounded. The curvature operator is bounded. The area gap is a prediction of the quantum gravity. So it seems that the singularity resolution, at least at the as concerned the kinematical aspect, seems to follow from the quantization of GR by gravity. However, I noticed that these, kind of like these parts can be maybe contested in a sense of like, this is the way in which the curvature is normally represented. But one can say, okay, maybe we can kind of like provide a different representation of the curvature. Even though I must say that I think it's like, I don't want to contest this assumption, but I just want to point out that it's kind of like an additional assumption, kind of like hidden maybe in the mechanism. So like the way in which the curvature operator is represented is not something kind of like prescribed by the theory. But I still think it's a reasonable physical assumption because it's sort of like what we do with the, well, it's analogous to what we do at the classical level. It's just that we don't take infinitesimal holonomics. What about the dynamical resolution? Well, in the case of the dynamical resolution, the dynamics of the theory crucially depends on the choice of symmetry reduced models. So again, it seems like in the mechanism there is my bad. It seems like in the mechanism there is a kind of like hidden additional assumption, which has to do with the fact that loop quantum cosmology is defined in the cosmological sector. So the only, I mean, why also, like, let's say from a historical point of view, like why do people start to study loop quantum cosmology? It's like, especially because the dynamics, so the Newtonian constraint was not solved at the level of the full quantum theory. So the only way to actually solve the Newtonian constraint to get understanding of the dynamics was to use symmetry reduced model. And as a matter of fact, the exact solution in loop quantum cosmology are still those of symmetry reduced model. I mean, there are some solutions that are maybe not completely isotropic, so they also have anisotropies, but it's mostly like very, very simple models with very few degrees of freedom. So one can kind of like question this point, maybe say like, oh, okay, but like the singularity resolution is just a feature of the symmetry. And it's fun because it's kind of like analogous to what was done at the beginning when they found out singularities. The criticism was like, oh, the singularity, for example, in the Schwarzschild metric, is just due to the symmetries of the model. And then Penrose proved that actually this is kind of like a generic feature of GR, even without the symmetry. So the point is here, we have kind of like the reverse. So maybe someone can say like, oh, the resolution of singularity is just due to the symmetry of the model. But it seems like we have good reason to think that actually like, this can be generalized kind of like in the same way in which the presence of singularity generalized in GR, in the sense that singularity resolution doesn't seem to depend on the assumption of symmetry. It's just that these are the models that we kind of like have a good manipulation on. So these are the models that we can exactly solve. But there is not like the symmetry doesn't play any role in how the mechanism is applied. Maybe play some role in how the Hamiltonian equation actually, take form. But it seems like we don't have good reason to think that the symmetries are play a crucial role in the singularity resolution. And as a matter of fact, like right now there are people studying the resolution, for example, of the Big Bang singularity, also implementing other techniques. So outside loop quantum cosmology, for example, using like spin flow in cosmology, so other let's say development of loop quantum gravity. So what about, okay. So this is kind of like how the previous analysis was applied to the case of the solution of the Big Bang singularity. So a study, let's say, a discussion of the assumptions and the conditions, and whether the assumptions are kind of like to be trusted or not, like say maybe not justified, but like set reasonable or not. And I think like it seems like this is a reasonable thing, and I would say like also the result of singularity resolution of the Big Bang singularity resolution in loop quantum cosmology is quite generic and robust. So it seems like, at least in the case of the Big Bang singularity resolution, like the resolution really follows from the theory itself. What about other types of singularities? So the singularity resolution in loop quantum gravity concerns only curvature singularities. As said before, specifically the Big Bang and black holes. What about the other singularities that I presented at the beginning, those that are geodesic incomplete, those spacetime that are geodesic incomplete, but in which there is no curvature law. It seems like actually quantum gravity doesn't have anything to say about the singularity in a sense, because we've seen that the singularity resolution seems to kind of like, maybe not directly, but like seems to depend heavily on the discreteness of space-time. So it seems to depend on the way in which the operators are bounded and so on and so forth, which it doesn't seem relevant in the case of incomplete geodesics without any law. But still, there might be a kind of like indirect resolution. So instead of replacing the singularity as quantum gravity does in the case of curvature singularities, it can be the case of adopting the other strategies that I presented at the beginning, the other way to understand, the other way to apply, or to, let's say, manifest singularity resolution that I presented at the beginning, which is in terms of preventing the singularity behavior to adapt. And actually, it's not, I mean, this is kind of like realistic possibility in the sense that the rising of singular behavior might be prohibited by the imposition of some interior constraint. And in the specific case of quantum gravity, these constraints can be the constraints that we must apply when we quantize space-time. So, for example, I mean, in quantum gravity, in order to quantize space-time, we need to put the GR in this Hamiltonian formulation. And this means that the space-time must be foldable. So, for example, like all the non-foldable space-time are kind of like ruled out by Fiat when quantized. They're not considered like a physical possible solution. So there is a restriction on the solution space of GR when we do the quantization. So it might be the case that the other singularities are ruled out in this way. So they're just like they're ruled out because they're not those space-time that are physically exist. But I'm not claiming that like this is actually the case. And actually, I think like this kind of like one of the limits of singularity resolution. So it's not clear, for example, well, in the case of quantum gravity, how it can actually solve like all types of singularities that we find in GR. So like it's clear how you can find like curvature singularity. Well, it's clear. We can claim that you can solve curvature singularity because of kind of like the effect of the quantum geometry. But what about those singularities that should be solved by preventing the rise of singular behavior? It seems like it's difficult to determine the extent of this strategy, and also like find like kind of like criteria for evaluating the strategy in the same way as I did for the other strategy, for the replacement strategy. Another limit is of singularity resolution is also how to understand the recovery of space-time in the replace strategy. So basically how the question of the like what happened when we take the semi-classical limit, how this relates to the kind of like solution of the singularity. Another limit is what is the fate of space-time singularity in quantum gravity. This is maybe kind of like related on also what is the attitude that we should take when we talk about space-time singularity. And then there are some technical limits that are just related to the fact that the theory is not, I mean, it's not fully established yet. And also like there are actually like different, like within the theory, there are kind of like different strategy to solve the dynamics, so the covariant approach, the quantum cosmology approach, and so on and so forth. So as a matter of fact, like how express the dynamic of the theory is not clear, like super clear. But I think like some of these issues can be addressed, or at least can attempt to address them. So in particular, the second one, so how should we understand the breakdown and the recovery of space-time with respect to the classical quantum level? So in the literature, you see like they claim that the effective space-time is geodesically complete. So when we quantize the singularity model, we get to the non-singularity model. We can express, well, in the case of quantum cosmology, the quantum evolution, and then from this quantum evolution, we can take the classical limits. What we get is a modified Friedman equation that is actually like non-singular. So it seems like this is kind of like the picture they have in mind. The question is like, how should we understand like then the relation between the two? Like in what sense? Of course, there should be some similarity, but they're clearly not the same model because one is singular, one is not. And like, in what sense we are really like kind of like replacing the singularity? So like if the replacement happening at the like quantum level or at the classical level, and how this all play out. So I think it's kind of confusing also because it's not clear like at what we care about when we are like asking this kind of question. I think like the third point, which is like what's the fate of space-time singularities? I think for that we can kind of like provide a more precise answer in the sense that even if actually like at the level of at the physical level, it's not the case that all the effective space-time are genetically complete. If what we care about here is the emergence of space-time, which is something like it's often talked about in the quantum literature. So the idea that yes, space-time might not be fundamental, so it could be the case that at the quantum gravity level, everything is not spatio-temporal, but we still need space-time to emerge at the classical level. If this is what we care about, and the question is like what happened at the classical level according to this kind of like emergence of space-time, then I think that the answer is that it should be understood that like, well, singularities or the singular structure is not an emergent feature in the sense that it's not emergent in the sense of like it's not one of these features that we really want to recover when we want to recover space-time. Because, as I was saying before, it seems like the singular structure is like the breakdown of the theory. It's like a wrong prediction of general relativity. So why should we want to recover it? And actually, so I argue in the paper that even at the fate of the singularity is that at the say ontological level, they're not even an emergent entity. So it's still present, the singular structure, but just at the level of the mathematical theory of GR. Yeah, so the singular structure would be at most a property of the mathematical model, not of the emergent field. So to conclude, what I've done in this talk is to specify what singularity resolution means. So they say that there are two different ways in which we can understand the avoidance of singularity. One is kind of like direct replacement. The other one is just by preventing singular behavior to arise in the first place. I individuated 3 criteria to assess singularity resolution. So kind of like what a theory of quantum gravity must do to actually claim that the singularities are solved. And then I analyze a specific case study, so the Big Bang singularity in quantum cosmology, and kind of examine how these criteria apply in this case, and then and discuss whether the mechanism of the quantum cosmology follows from the principle of the theory. If yes, to what extent, and like what are the other kind of like hidden assumptions in play. Thank you very much.